Hi, welcome to section 7.8, improper integrals. Now, what is an improper integral? Okay, it extends the concept of definite integrals to integrals over an infinite interval and integrals in which the integrand becomes infinite within the interval of integration. I know some of you are thinking, what? I'm pretty sure that wasn't English. Well, it was. So basically what an improper integral is it kind of looks like it's trying to be a definite integral, but something's gone wrong. Remember, a definite integral is something that you have a nice, pretty continuous function, and you're going from a number to a number, okay? A finite to a finite. So you are finding the area under that curve, and there is a specific area. Now, the first example, the integrals over an infinite interval, that just means infinity is one of those limits. It's either the top limit or the bottom limit, or perhaps it's the top and the bottom limit. The second type, integrals in which the integrand becomes infinite within the interval of integration, okay, just so we know what that means. When you look at the limits 0, 4, it looks like it is a normal definite integral. But remember, this guy has to be continuous on the interval. Something bad's happening at x equals 2. X can't equal 2. There's an asymptote there. So from 0 to 4, we have a spot inside there where we are not continuous on that interval. So what we're going to do is we're going to use limits to find the answer, if possible. All right, so we're probably thinking, if possible, what does she mean by that? Well, what we're going to do is, in this first case, we've got infinity as our top limit. So we've got some number on the bottom. We're going to take the limit and we're going to assign this infinity a variable. And in this first example, I apologize because I used L. That's usually not a good idea because L's look like 1s. So we're going to let that infinity equal L, and I'll make it cursive as I did down here so that you can maybe tell the difference between them. Instead of just taking the integral, we're going to take the limit as that top goes to infinity, and now it looks like just a normal, regular, old integral, which we will integrate, and then we'll plug the L in, minus, and then we'll plug the A in, and then we'll take the limit and see where that limit's approaching. If the limit exists and it approaches a number, then we're going to say that improper integral converges, and we're going to tell them what it converges to. If the limit does not exist, it has no bound, left side doesn't equal right side, etc., then we're going to say it diverges, which means it will not have an answer. So when we look at our first example here, number 1, we can see that we have that first type of improper integral where we have infinity poking out somewhere. So we're going to rewrite it. So this is what we started with. We're going to rewrite it as a limit. So the limit as L approaches infinity, and you can literally pick anything you want right here. So we're going to change that top limit to an L, and then we're going to integrate this just like we've done before. And when we integrate, that means every possible thing we've ever used as a technique for integration is something we're going to be able to use again. Now, are they going to use really, really bad integrals? No. So you're probably not going to have a trigonometric substitution here. So we integrate 1 over x squared, which is x to the negative 2. So we integrate that as x to the negative 1 over negative 1. We're going to plug the 1 in, or the L in first, and then we're going to plug in the 1. So this is what we get. And we're going to take the limit as L approaches infinity. Well, as L approaches infinity, well, what happens to a fraction when the denominator gets really, 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 really big? That fraction is going to go to 0. Negative 1 divided by 1 is negative 1, but you're subtracting that, so you get plus 1. So 0 plus 1 is 1. You got an honest-to-goodness answer, so that's what your integral is equaling. Because you got an honest-to-goodness answer, we're going to say that that converges. So not so bad. You're just kind of joining limits together with pretty nice integrals. I'm not going to say they're going to be super duper nice all the time, but you're not going to get the crazy, crazy, crazy things. All right, so number 2, pretty much the same type of example. I am going to rewrite this. I'm going to rewrite it as the limit. I'm going to just choose m. As m approaches infinity of my integral from m to 1 there, dx over x. Okay, so I'm going to integrate. Dx over x is the natural log. So that's the natural log of the absolute value of x. We're going to put m in first, and then we're going to put 1 in. So you're kind of on autopilot until you get to this step. Okay, so you integrate just like you've always done. Plug the top number in first, then the bottom number in, first fundamental theorem of calculus, and now we're going to see what happens. Well, what's the limit, or what's the limit? What's the natural log of 1? If you said 0, you are correct. So we've got the natural log of infinity minus 0. Okay, that's going to infinity, which means it does not exist, which means this guy diverges. Okay, so not too bad. One last example in this little possibility here. Same thing. We are going to rewrite the limit as m approaches infinity, going from 0 to m, of x e to the negative x squared dx. Well, when I go to integrate this, I'm going to need a u substitution. Okay, so I'm going to let u equal negative x squared. So that means du is going to need to be negative 2x dx. I have the x, but I don't have the negative 2, so I'm going to put that in. I'm going to counteract it just like I've always done. Now, the difference is we are not going to change these limits here. We are going to leave those as they are, which means when I integrate this, I'm going to have to switch back to the x's before I plug in the m and the 0. This becomes e to the u du. When I integrate that, I'm going to have 1/2 e to the u. I did not change my limits, so I'm going to substitute back. Before I put the m in and the 0 in. Okay, so that's going to be the limit as m approaches infinity of 1/2 e to the negative m squared minus 1/2 e to the negative 0 squared. Okay. Well, when you have a negative exponent, we always like to flip that over. So that'll be 1/2 e to the positive m squared. This is just going to be 1/2 because e to the 0 is still 0, or still 1, sorry. Now when we're looking at this guy right here, if I put in a big number and I square it, that's going to be a big, big number. E to a big number is going to be a really, really big number. Denominator keeps getting bigger, bigger, bigger. That fraction's always going to go to 0. Okay. All right, so I end up with, oh, I lost my negative. How did you let me do that? See, this is why we need to be in class so I don't lose my negative. Okay, so that's going to give me a positive 1/2. So that negative 1/2 I had out there, somehow I lost my negative. So therefore, my integral from 0 to infinity of x e to the negative x squared dx converges, and it converges to 1/2. So now let's try a couple of examples where we have infinity on the bottom. We're not going to do a lot of these examples, so I'm going to leave a couple for you to do, or at least one for you to do, because it's the same exact concept. You're going to rewrite this as the limit as whatever. You can still use m. As we approach negative infinity, you're just going to put that m in there. And then you're going to integrate, just like you did before. So the integral of e to the x is e to the x. We're going to put 0 in first and then the m. Remember your first fundamental theorem of calculus. Now if we put in negative infinity, what we have here is going to be a negative exponent. So e to the 0 is 1. I'm going to have 1 over e to a really big number, which is going to go to 0. So the whole thing's going to go to 1, which means we converge. Okay. I'm going to save this example for you to do. You're going to need a u substitution, and just as a hint, u is going to be 3 minus 2 e to the x. Okay, but I want you to try this one. You'll be fine. I'll give you the answer in class. Now, what happens when we have negative infinity to positive infinity? Well, we have got to break it up. So there's got to be a number in between negative infinity and positive infinity. Oh, there is. We're going to use our friend Mr. Zero. Okay. Now in this case we do have to use a different letter here. So we're going to do the first integral just like we did the last examples. We're going to do this second integral just like we did the first examples. Okay, so notice we had to do 2 separate limits. You've got this first guy here, that's this guy, and then you do the second one, which is this guy. Now, both limits must exist for the integral to converge. Okay? It doesn't have to go to the same thing. Okay? For instance, if this is positive infinity and this is positive infinity, you're going to converge or diverge. If this is positive infinity but this goes to a number, sorry, you're still divergent. Okay? So it's, excuse me, it's not enough that you go to positive, positive. You can't have infinity of any kind. All right, so we're probably going to need 2 slides for this. Here we go. We're going to split it up, going negative infinity to 0, and then from 0 to positive infinity. And I'll use M and P, so we're not using our L there. So the limit as m approaches negative infinity, we're going to have m to 0 of x dx square root of 2 plus x squared plus the limit, I'm just going to keep the same color, limit as p approaches positive infinity. Oh, p for positive, oh, I should have used n for negative. Dang it. I'll know to be more clever next time. Okay. Now I know probably some of you are moaning and groaning going, oh my gosh, look at what we have to integrate. It's going to be the same integral. You're integrating x dx divided by the square root of 2 plus x squared. It's the same thing. So once you integrate it, you'll be fine. Okay, so looking at this, we would do a u substitution. We're going to let u be 2 plus x squared. Du will then have to be 2x dx. Neither one of them have an 2x, so I'm going to put it in, which is going to cost us a 1/2. Put it in. It's going to cost us a 1/2. I'm going to rewrite. And remember, since we are not changing our limits, we have to substitute back before we plug in our m's, zeros, and p's. So this is going to be du over the square root of u, or u to the 1/2 power down there. Same thing here. P, we've got 1/2 power. So when I integrate this, I've got the limit as m approaches negative infinity of 1/2. Okay, if I integrate u to the negative 1/2 power, that's going to be u to the positive 1/2 power, so I'm going to have to multiply by 2, u to the 1/2 power. We're going from m to 0. Same thing here, because it's the same integral. We're going from p to 0. Okay, so we're going to substitute back. Okay, so we've got the limit as m approaches negative infinity. The 2 and the 1/2 cancel, so I have square root of 2 plus x squared going from 0 to m, plus the limit as p approaches positive infinity of the square root of 2 plus x squared, eq p to 0. Okay. I'm going to go to the next slide. Hopefully it is blank. And I'm going to plug those values in. So this first guy, I get the limit as m approaches negative infinity. I put that 0 in first. Well, 2 plus 0 is 2, so I get the square root of 2 minus 2 plus m squared. And then I've got plus the limit as p approaches positive infinity. Here I've got the square root of 2 plus p squared. And then I've got my minus my square root of 2. Okay. Hold on, let's see what we have here. So we've got minus, yes, okay. Okay. So when we look at that, we've got problems. Okay, yeah, we've got a square root of 2 here, but look at what happens right here. We've got 2 plus negative infinity squared, so that's going to be a positive number. You've got 2 plus a big, big, big number and you're square rooting it. That's going to be negative infinity. Okay, over here, I've got a big positive number squared plus 2 square rooted. That's going to be positive infinity. And remember, think about infinity as a destination. You're going to reach that destination at different speeds. So we cannot say negative infinity plus positive infinity is 0, because we're going to get to our locations at different speeds. So these are not always going to be equal. We have no idea what they're going to be. Because one of them or a part of it equals infinity or negative infinity, we can say this little guy diverges. Okay? Doesn't matter about our little square roots of 2. Doesn't matter if one of them went to a number. If the other goes to infinity, it's a divergent situation. Okay. Okay, I'm going to leave that one for you to do. This is going to be another little u substitution when you split that one up. So I'm going to leave that one for you to try. Okay. And then we get to the ones that look normal, but they are abnormal. All right, so when I look at this guy, I'm going from 0 to 8. 0 to 8 looks perfectly fine, but there's a problem. There's a problem at what number? There's a problem at 0. So 0's the number I'm going to have to get out of there. Okay, so I'm going to take the limit as m approaches 0, okay, because 0's that bottom limit, and I'm approaching it from the right side, and I'm going to go from m to 8. Okay, so I'm going to look at my dx over x to the 1/3 power, so that's x to the negative 1/3 power. I'm going to integrate it. Okay, m8. I'm going to integrate it. I don't know why I don't listen to myself. So when I integrate that, I get 3/2 x to the 2/3. Okay, so I'm going to plug in those limits. I'm going to perform the first fundamental theorem of calculus. So 3/2 8 to the 2/3 power minus 3/2 m to the 2/3 power. Well, m, we're putting 0 in there. We're approaching 0, so that's gone. So I just need to figure out what 2/3 8 to the 2/3 power is. Did I say that backward? 3/2 8 to the 2/3 power. So 8, if I take the cubed root of it, it's 2. Squared, it's 4. 3/2 times 4 is 6. So it converges. Okay. So here my problem area was at 0. It was at one of those limits. Okay, now another example, our last example. It's that one that we had at the very beginning of the slide. This we have a little problem. This is where we have a problem. We are not continuous at 2, which is smack dab in between. So we're going to have to split this up. So we're going to go from 0 to 2 of our dx, and then go from 2 to 4. So we have to split up that crazy point. And then, of course, we will have to do 2 actual letters there. So we'll have to pick the limit as m approaches 2 from the left side. So that'll be 0m dx over x minus 2 to the 2/3 power, plus the limit as p approaches 2 from the right side, p4. Okay, so we are going to integrate this, and just like before, it's going to integrate the same way. We're going to do a little baby u substitution. Okay, where did that 2 come from? Goodness gracious, you got to watch me every minute of the day. Okay, so I think I had that 2 there. X minus 2 to the 2/3. Both of what's inside the integral, the integrand, should look exactly the same. The only difference is you have an m here, you have a p here. All right, now we're ready for a u substitution. U is going to need to be x minus 2. Du is going to be dx. So this goes right into our nice pretty form. So what's inside that, or what your integrand is, it's going to be from 0 to m, and that's going to be u to the 2/3 power on the bottom, so u to the negative 2/3 if I want to bring it on top. P to 4, u to the negative 2/3 du. Okay, so when I integrate this, I'm going to have the limit as m approaches 2 from the left side. I'm going to have u to the 1/3 times 3, so 3 u to the 1/3. Remember, I didn't change these limits, so I'm going to have to substitute back before I can plug values in. Which means I'm going to have to go back to this. Ooh, this problem is red. Okay, so I've got x minus 2 to the 1/3 power. I'm going to put the m in first and then the 0, plus the limit as p approaches 2 from the right, 3x minus 2, 1/3 power. Ooh, going to put 4 in and then p in. All right, so we get the limit as m approaches 2 from the left side of 3 times m minus 2 to the 1/3 minus 3, 0 minus 2 to the 1/3. Okay, then plus the limit as p approaches 2 from the right side. Okay, that 4 goes in first, so I have 3 times 4 minus 2 to the 1/3 minus 3 times p minus 2 to the 1/3. All right, so as I approach 2 from the left side, this guy is going to go to 0. So this guy's going to go to 0. Okay. This guy, oh, let me write it out. So this guy's going to be -3, -2 to the 1/3 power. Okay. Now, when you have a -2 to the 1/3 power, that's the same thing as negative, or let me see how I can write this without taking too much room. It's just like -2 to the 1/3 power. So it's the same thing. So you end up with 6 times 2 to the, oh, jeepers creepers. I'm going to go home after this. So you end up with +3 cubed root of 2. Okay. When I go over here to this limit, as you put in 2 here, you're going to get 0. This guy is going to be 3 times 2 to the 1/3 power. You're adding. So this is going to be 3 cubed root of 2. So you have 3 cubed root of 2 plus 3 cubed root of 2. You've got 6 cubed root of 2. Okay. So once again, right here, you had your -2 to the 1/3 power. You can put the negative on the inside of that cubed root, or you can put it on the outside. We prefer to put it on the outside because you had it negative already. Okay, that way it canceled out and gave you a +3, and then the cubed root was the same as this cubed root, so you could combine them. Because you did get this nice pretty answer, you know that it converges. So be careful when you're looking at definite integrals from this moment on. Okay, the first type are not hard to see. You see infinity in there as one of those limits, you know you got trouble. But this little guy in example 8, those are sneaky. You've got to be paying attention to, is the integrand continuous on this interval? If it is, go right on ahead and integrate. If it isn't, you're going to have to split it up and incorporate limits. Limits and integrals. Ooh, we've been doing, oh gosh, we've done everything. Remember the 3 prongs of calculus? Limits, derivatives, and integrals. We did limits, we did derivatives, and we did integrals. Oh my gosh, these problems complete me. I'll see you in class. Bye.